My name is Chuck Gershman. I am CEO and co-founder of OWL Autonomous Imaging. Our team here at OWL has designed some of the world's most advanced thermal cameras for military and space application, and we're now addressing dual-use applications for automated perception with our novel patented no-light thermal 3D computer vision system. So I'm going to show you a quick video here to highlight what we do. This is specific to the automotive market, but this is dual-use technology. So go ahead, run the video.
Chuck, I'm just going to optimize it for a sec so it runs smoother. So just bear with me 1 second and we'll have it up.
At OWL Autonomous Imaging, we're all about safety. We use thermal imaging and custom thermal ranging software that allow us to detect pedestrians and range to them and locate them for autonomous automobiles so that we can have automatic emergency braking for pedestrians and to save lives.
Adding a thermal camera to an automobile for safety purposes extends the range of operation over using just visual cameras.
There are lots of low-light cameras, but thermal imaging is a no-light camera. So it can see pedestrians, it can see cars, it can see buildings at night with absolutely no light.
We combined an advanced thermal imaging camera with custom optics and artificial intelligence machine learning software to produce a 3D thermal image for use in automobiles to make driving safer.
We're an input to the system to tell it where there's a threat. The car will decide, hey, there's a pedestrian or animals, and either steer away from it or brake. Radar and LiDAR have difficulty with pedestrians between parked cars because they see the car first and they don't see the pedestrian. And because we're thermal, pedestrians really pop out of the image. There's no difficulty finding pedestrians or deer behind bushes. Anything that's warm-bodied just really pops out of the images. Our main target market is automotive, ADAS, and AV, but it also could be applied to other existing markets such as first responders, firefighters, and search and rescue. Obviously, it's always a good thing if you can save a life.
Today, in the United States alone, 6,000 pedestrians will be killed by cars. 76% of those pedestrians will be struck in poor lighting conditions, so nighttime or dusk or dawn. And the numbers are not decreasing. We solve that problem. We save lives, save lots of lives.
Okay, next slide, please. All right, so that gave you a good idea of what we do. And again, this is a dual use capability. In addition to no light, these are other conditions where thermal cameras are not negatively affected and visual cameras are. So all of these conditions a thermal camera can see quite well. So the market for what we're doing, our target markets are automotive, defense, traditional 2D thermal markets, as well as industrial heavy equipment and mining. This all adds up to an opportunity of about a $10 billion servable market, SAM, and a 37% CAGR. Next slide, please. Next slide, please. Sorry. All right, so our solution is disruptive. We're the only monocular thermal imager that operates in 3D. We have developed the world's first megapixel thermal sensor at commercial price points, and in a few years, we'll introduce a thermal sensor at the price of visual. Next slide. Early revenue comes from mature non-automotive markets, as we just discussed, where we already have design wins. We realize, next slide, please. We realize our billion-dollar potential via automotive penetration, where a design win with a single tier 1 systems manufacturer begets numerous OEM wins. And today we have pilots with Hitachi Auto and Honda, and have pending deals with all the companies denoted by the yellow check mark shown on the slide. Next slide, please. Within defense, we've secured over $3 million in contracts with another $800,000 in the pipeline for off-road application of our technology, specifically with the US Army and the National Science Foundation. This image here shows you the off-road capability. I should highlight that our solution is completely passive, so we enable stealth operation. And I also added a testimonial from one of the soldiers who evaluated our capabilities. You can see that in the blue here. Next slide, please. Versus the competition, we support both object identification and location in infrared. Our competitors only support identification, not location. And then on the y-axis, aspects of high quality include resolution, frame rate, sensitivity, dynamic range, and field of view. And again, simply stated, no other infrared competitor is addressing 3D depth perception. Next slide, please. Okay, so finally, why are we here today? Well, one, we're looking for additional ground vehicle partnerships within the federal market, specifically not simply with government directly, but with system integrators. Two, we continue to look to grow our OEM and Tier 1 automotive relationships. And finally, we're nearing closure of our Series A equity round, and we have an additional allocation of about $3 million that's still available to top off our round. So any of the investment community out there, we'd love to talk to you. And with that, I'd be happy to take slides. Next questions. Next slide. There we go.
All right. Thank you so much, Chuck. Bob, you raised your hand first. Go ahead.
Okay. Chuck, nice to meet you. I'm surprised we haven't had a chance to meet before. Actually, I worked at Panasonic in charge of advanced engineering. We did a lot of modules around cameras. Anyway, I'm curious about how you can train the data. So you had thermal imaging. I saw, obviously, you're using, it sounds like IMU data to get the 3D distance. I'm wondering then, how can you take that data and fuse it, if possible, with the RGB data from a camera to then learn and understand if that is a specific person and if they're old or if they're young, because then a car can behave differently, right? So if the car knows a person's fast, they're a runner, they're a jogger, they can then say, okay, I'm going to maybe slow down, but not stop. If somebody's walking across, this is something that I've a discussion that I've had with a couple of the Tier 1s, and they're trying to solve some problems. So I just curious about the training of the data and anything you could, any information you can provide.
All right, that was quite a bit there in that question. First premise, yes, we do train. We train both temporally and spatially. So for temporal training, we use a combination of IMUs and CNNs working together, because the IMU data sets unto themselves are not quality enough, at least low-cost IMUs. I mean, if we used a full-on gyroscope, that would work fine, but it's not really cost-effective. So we use a combination. We also operate spatially. So single frame produces depth through the generic term for the algorithm is monodepth. So that's a different training sequence than the temporal. So we use both, we combine them. As far as fusing a thermal with RGB, that is actually on our roadmap, and we'll probably be demonstrating that sometime in the next couple of quarters. It's actually not that difficult a process to fuse the thermal and the RGB together. One question is whether you start with RGB and fuse thermal, or you start with thermal and fuse RGB. More than likely, the thermal data is actually higher quality in some ways than the RGB, or less ambiguity. So we'll probably put the RGB into the thermal as opposed to the thermal into the RGB. But we already do some of that today for training purposes. So we use RGB data for training. So we do. So we actually use RGB data sets and train on them, and then map them over to thermal as well. So I don't know if I answered all of your questions.
Well, you did.
In terms of the recognition,
yeah,
we don't currently have a plan to classify based on age. We are classifying based on height and kind of height and weight, but we could certainly classify on some other metrics if necessary.
What is your timetable to get to price parity with a regular camera system, if that's even possible?
Well, I don't know if we'll get ever to complete, well, to get to complete price parity is a little bit of a stretch. So there's basically two main components from a cost point of view. One is the sensor, which, as I said, in 18 to 24 months, we think we can get the sensor price down, and we have some patents on this, very, very close to an RGB sensor. We can't change the lens structure that dramatically, and we don't actually build we design lenses, but we don't actually manufacture them. So the lenses will going to a pure plastic lens or a polymer lens is not in the near term So the lens is always going to be a little more expensive than the RGB lens, at least for the foreseeable future, until
That's
polymers come along.
Thank you for that. That's an area that we're working on, by the way, at Mitsubishi Chemical. Lenses for sensors and to bring down price parity. So we can talk about that later if you'd like.
I'd love to. That's a real important, major problem from a pricing point of view to fix.
Perfect. Dana, go ahead.
Yeah, my question was about power consumption. I mean, historically, LiDAR has been power hungry and it's caused headaches for autonomous systems in ground vehicles. And I wonder, could you speak to the kind of power consumption parameters of this thing?
Sure. So first off, we are a receiver, not a transmitter. Hence my comment about it being purely passive. So first off, just basic mathematics, we only have half the circuitry of a LiDAR system, just at the 30,000 foot level. So right there. In addition, one of the things that we've done really differently than anybody else that makes up a preponderance of our patents is traditionally thermal sensors are built using analog CMOS components. So it's an analog ASIC, predominantly analog. Analog generally uses older technologies and very high speed analog to digital converters. We flipped the industry on its head. We've digitized our thermal imager. It's almost completely digital. So we digitize at receipt of energy, which gives us a digital circuit, which allows us to, instead of building chips at 180 nanometer power hungry process nodes, we're at 22 nanometer, super power sensitive. We have we're about 20 to 30 times less power per sensor than an analog equivalent. So our sensor system is significantly less power. And again, we're only a receiver. So compared to LiDAR, it's apples and oranges from a power perspective.
Are you considering working with any aviation, because you've got that third dimension? Autonomy may be easier to achieve when you've got that third dimension and you're working in an aviation context. Are you talking to anybody either in advanced air mobility or some of the traditional OEMs?
All right, so there's what the technology can do, and then there's how big the company is and exactly how much we can focus on. So since we do artificial intelligence, we're somewhat application specific. So we have this thermal technology that's applicable across a wide scope of application. But when we add the AI capability, it's specific to kind of subsets or individual niches. So yes, working in an avionic environment, unequivocally doable. It just doesn't happen to be. We just don't have the current staffing to focus on that today. Unless, of course, someone funded us in such a way that you asked us to kind of change direction, right? But it's certainly applicable.